The Shenyang J-50 fighter program, while aggressively promoted by Chinese state media as a significant leap in military aviation technology, faces a myriad of fundamental challenges that seriously call into question its real-world effectiveness and strategic utility. The fact that it is still at the prototype or experimental phase severely limits its credibility as a fully capable next-generation stealth fighter. The leap from prototype to operational frontline asset is fraught with technical and practical challenges, and history shows that many such ambitious projects worldwide fail to fulfill their intended roles. The J-50, despite all its hype, is very much still an unproven concept. Starting with the aircraft's aerodynamic design, the J-50 departs from proven stealth fighter configurations by adopting a tailless lambda wing layout combined with full-moving wingtips instead of conventional vertical and horizontal stabilizers. While this configuration is innovative, it carries serious trade-offs. Traditional tail surfaces play critical roles in providing stability, control authority, and maneuverability, especially at high angles of attack or during rapid combat maneuvers. The removal of these surfaces puts a heavy burden on the wing control surfaces to compensate, potentially leading to compromised flight stability or increased pilot workload. Moreover, this design choice may make the aircraft more susceptible to control surface damage, with fewer redundancies built into the flight control systems. In a combat environment where damage tolerance is crucial, this represents a vulnerability. Also, achieving the right balance between stealth shaping and aerodynamic efficiency is notoriously difficult. The J-50's unconventional layout may force compromises that reduce either stealth or agility. The engine technology powering the J-50 is another major concern. China's domestic jet engine industry has historically struggled to produce reliable, high-performance turbofan engines comparable to Western counterparts like the Pratt & Whitney F-119 or General Electric F-110. Although improvements have been made, China's engines often suffer from lower thrust-to-weight ratios, reduced fuel efficiency, and shorter operational lifespans. These limitations translate directly into reduced range, payload, and combat endurance. The J-50's promised thrust vectoring capabilities, while theoretically enhancing maneuverability, are complex and demanding on engine design and maintenance. Without mature engines, these advanced features could be unreliable or severely maintenance-intensive. Sensor and avionics integration is another area where the J-50 likely falls short. Modern air superiority fighters rely on a highly integrated sensor suite: radar, infrared search and track, electronic warfare, and communications systems, all fused by advanced software to provide pilots with unparalleled situational awareness. Chinese aerospace firms have made strides in radar development and sensor miniaturization, but their software integration, cyber resilience, and electronic warfare capabilities still lag significantly behind those of Western and even some regional competitors. This lag likely affects the J-50's ability to detect and track threats at long ranges, resist jamming and electronic attack, and coordinate seamlessly within a larger networked force. Without these capabilities, the aircraft's survivability and lethality are compromised, especially in contested airspace against sophisticated adversaries. The stealth capabilities of the J-50, while visually emphasized, are also questionable. Achieving true low observable, low characteristics is an extremely complex endeavor that involves not just airframe shaping but also materials science, coatings, and internal weapon carriage. China's ability to manufacture and maintain advanced radar-absorbent materials consistently and reliably under operational conditions remains unproven. Moreover, stealth coatings require constant maintenance and are vulnerable to environmental wear and battle damage. Any degradation in these materials drastically reduces the aircraft's stealth effectiveness. Additionally, the internal weapons bays, critical to preserving stealth profiles, have yet to be demonstrated with operational munitions in realistic scenarios, leaving doubts about the J-50's true stealth combat effectiveness. Maintenance and logistical support represent another glaring challenge. Stealth fighters are notoriously resource-intensive to maintain, requiring specialized facilities, trained personnel, and complex supply chains. China's defense industrial base, while growing, still lacks the depth, experience, and robustness of established Western systems. The J-50's advanced technologies and unique design features likely increase the maintenance burden, reducing sortie rates and increasing operational costs. Prolonged conflicts would expose these weaknesses, potentially grounding significant portions of the fleet when they are most needed. Pilot training is a further concern. The new aerodynamic and control characteristics of the J-50, combined with its complex avionics, will demand extensive and sophisticated training to operate effectively in high-threat environments. China's pilot training programs, while improving, have not yet demonstrated the capacity to produce large numbers of highly skilled fighter pilots comparable to Western air forces. The gap in pilot proficiency could negate many of the theoretical advantages the J-50's technology might offer. Operational doctrine and integration issues also deserve scrutiny. Advanced fighters do not operate in isolation, their effectiveness depends on integration with ground control, airborne early warning systems, other aircraft, and wider military networks. China's command, control, communications, computers, intelligence, surveillance, and reconnaissance C4ISR infrastructure remains under development and faces significant challenges in achieving true jointness and interoperability. The J-50, no matter how advanced on paper, risks being hampered by a lack of operational synergy within the broader force structure. Finally, there is a strategic dimension to consider. The J-50 appears to be as much a political and propaganda tool as a military asset. Its public unveiling and media coverage serve to project an image of technological prowess and strategic parity with established air powers. However, diverting substantial resources to a high-profile but immature program may detract from more practical investments in mature technologies, fleet modernization, and readiness improvements. The focus on symbolic prestige aircraft can lead to hollow capability, flashy on the surface but limited in true combat utility. The Shenyang J-50 suffers from multiple fundamental disadvantages. Its unconventional aerodynamic design introduces control and stability risks. Its engine technology is unproven at the level required for sustained high-performance operations. Its sensors, stealth materials, and avionics integration likely lag behind proven Western standards. Maintenance, pilot training, and logistical support remain problematic for a complex platform like this. The aircraft's potential is further diminished by challenges in operational integration and strategic misallocation of resources. All these factors suggest that despite its ambitious appearance and aggressive promotion, the J-50 remains far from a credible threat to established air superiority platforms and may serve more as a symbol of aspiration than a real game changer in modern aerial warfare.